Okay, good morning, class. This is class number 38. Today we're going to look at designing a beam for a swing set. So what we have here is we have the cross beam over here, and we have three swing locations, all located about 3 feet apart. And we have a 250-pound load, a 250-pound load, and a 250-pound load hanging off of our cross beam right here. And what we're going to do is try to design what size does that beam need to be. Yeah, we could go to the lumber yard and pick out a 8x8 or a 10x10 beam, but that might be overkill and it would be expensive. We want to get the most economical beam for this swing set. So what we have here is, and as we've looked at the rest of this at the beginning of this semester, our reactions and our shear moment diagram. From our moment diagram, we are going to pick out what that maximum value is. So if we look at our beam up here, and I have those forces spaced about 3 feet apart, by symmetry, we can tell that the reaction on each side of the beam is going to be 375 pounds. And from there, we can draw our shear diagram. We go up 375, we go over, we go down 250 to about 125. We're going to go over, we're going to go down another 250 to negative 125. Constant shear in that area. Then we go down another 250 to minus 375. And then we end up back to 0. So we have our shear diagram. I didn't draw this to scale, but you can see we're going to have approximately 4 areas. We're going to have area 1, area 2, area 3, and area 4. If we look at this, area 1, we'll do this over to the side here. Area 1 is going to be positive 375 times 3 feet. And that's going to give us a value about 1125 pound-feet. So from our shear moment diagram, we would go up to 1125. Now area 2, we're going to have 125 times 3 feet. And that's going to give me 375 pound-feet. And if I add that to that value there, I get a value close to about 1,500. Once again, constant shear gives me there. And then I'm going to have a negative value. I'm not going to spend the time calculating that. And it's going to close out to 0. So from this, we can tell that our maximum moment is this value right there, 1,500 pound-feet. Remember, this example we're doing in pounds. We're not doing it in kip feet like we've done some of our other examples. This is going to be 1,500 pounds. So if we go back to our original equation, where stress equals m over s, or that equals the bending stress, FB. I'm going to give you guys the bending stress for the wood that we're going to be using. We're going to set that equal to 900 psi. So remember, this is in pounds per square inch. So if we put what we know 900 is my stress, and that's in pounds per square inch. That's going to equal my maximum moment, which is 1,500. And I have it right now as pound-feet. Remember, the units are going to be important when I'm solving for this problem. And I'm going to divide that by S. If you notice, I have inches squared in pounds on this side, and I have pounds in feet. And if you remember, S is typically in inches cubed. So I need to convert this pound-feet to pound-inches. So all I need to do is multiply this by 12 inches per foot, and the feet are going to drop out, and I'm going to be left with all pounds, inches, and inches. So from there, I can solve for S. S needs to be greater than or equal to 20 inches cubed. So from that, I can look at my tables, and we will have already looked at those. And from that, I can see that I need to use a minimum of a 2 by 10 to support this swing set here. And we will look at a further example. We're going to change this around a little bit and see what happens when I move my support conditions and see maybe we use a bigger beam or a smaller beam. But to summarize, we draw our shear diagram, we draw our moment diagram, we pick off the maximum moment value. We still use our original bending equation here, stress equals M over S. From there, we're given the stress of 900 psi. We pick the moment straight from our moment diagram, and then from there, we solve for S. Once we get S, we enter our tables in the back of the textbook, Appendix F, and we find a beam that has an S value at least greater than 20 inches cubed. Now, we could have picked a much bigger beam. We could have picked a beam that was 4 inches wide by 20 inches deep. That would have been sufficient for this problem. However, if we go to the lumberyard and we're looking to buy that material, that 4 by 14 is going to be much more expensive than this 2 by 10. So we want to find the most economical size when we are sizing these beams. All right, now we're going to look at a different example, or example 2. We have that same swing set beam that we had on example 1, except you can see I did one difference to this problem. I still have 3 feet, I have 250 pounds in, 6 feet, I have 250 pounds in, but I moved my support from the end of the beam and I moved it 3 feet in, so I have this short little cantilever here, and I'm going to still have that load of 250 pounds there near the end of the beam. And what we're going to show here is what happens when we move the supports around. We still have the same 250 pounds at 3 different locations, but we're going to see how this changes our moment diagram, and then in turn how it changes the beam design process. So these are things we need to think about when we're actually laying out the beam and where we're going to put these loads. So I've already gone ahead and solved for my reactions. I have here at the left side 194 pounds, and here at this interior reaction 556 pounds, both going up. So let's go ahead and draw our shear diagram. So I'm going to go up to 194. Going to go across. I'm going to go down to minus 56. Continue over. I'm going to go down to minus 306. I'm going to go over. Then all of a sudden, I have a positive shear, a jump, and that's going to bring me to 125. It's going to bring me to 250, and it's going to go over, and it's going to go down. So I can break this up into different areas here. If I take 194 times 3 feet, I get 582. If I take minus 56 times 3 feet, I get negative 168. If I take minus 306 times 3 feet, I get minus 918. And if I take positive 250 times 2 feet now, be careful, we didn't go the full distance of 3 feet, that's going to be plus 500. So if I draw my moment diagram off of that, I go up 582. I go down to this value right there. I go down to 414. I go all the way down. That minus 918 is going to bring me down over there, which I think you guys can still see. That's about minus 501. And then it's going to bring me back to 0 when I have my 500 pounds. And actually, it should have brought me to this point right there. But we won't worry about that. It closes out. So you can see from this, my maximum positive moment is 582 pound-feet. And my maximum negative moment is negative 101 pound-feet. So the maximum value, when we take the absolute value, is going to be that 582. So I'm going to go back and I'm going to use my same equation, that same stress of 900 pounds per inch squared. It's going to equal my maximum moment, 582 pound-feet. And I'm going to divide by S. I rearranged some terms, but I need to make sure I multiply this by 12 inches per foot. So the feet drop out, and I'm left with pound inches. And remember the units for this, still in inches cubed. And when I rearrange some terms, I get S now needs to be greater than equal to 7.76 inches cubed. Remember, from that previous example, we had an S of 20 inches cubed. So same beam, same loads. We just oriented the loads a little bit differently. We moved that reaction in, and now instead of needing 20 inches cubed for my S, I only need 7.76. So if I go ahead and look at my charts, I can use a 2 by 8 as opposed to that 2 by 10, which I needed for that previous problem. So give some thought on where we actually want to lay these out. Now maybe you're looking at this problem and say, hey, we don't have enough room here. Maybe we do need to put the support at the end. But if that's not a concern of ours, we can go ahead and change things around, and we can make it a 2 by 8 as opposed to that 2 by 10. Now I realize just one 2 by 8 and one 2 by 10 isn't that, the cost difference isn't that much. But now imagine we're doing a building and we have 1 million of these 2 by 8s or 2 by 10s, and each one is about $2 to $3 more. We multiply that by a lot larger number, the cost is going to significantly go up. So it is important to look at these things when we're doing the design. And this example here just showed the importance of moving these reactions around and what it's going to do and if it changes our final answer. Okay, welcome back here. We've already looked at bending. That was what we did for the last couple example problems. We also need to look at shear when we're looking at beam design. So we're going to look at shear. And what we're going to do is we're going to compare from Appendix F on page 499. There's a value in that table which is F sub V. And this value is going to be given to us, whether it's in a table or I give it to you guys. But the value is given, depending on the species of the wood that we're going to use. And the equation that we're going to compare that to is this equation here, where we have F for shear is equal to V divided by A times 1.5. So we take the maximum shear, A, the area of the beam, and we multiply it by 1.5, where we have V equals max shear. We get that straight from our shear moment, or our shear diagrams that we've been doing. A is the cross-sectional area. So if I have a beam that is 2 feet or 2 inches wide by 2 inches tall, it's going to be an area of 4 square inches. So it's the same process as bending here. So I'm going to go back to our simple example that we've looked at in a previous class here. We have a beam here that is 12 feet long, and we have a load of 2 kip per foot. So this 12-foot long beam, we want to do our shear diagram. Well, our shear diagram here, 12 feet times 2 is 24 kips going down. So each of our reactions we know are going to be about 12 kips. So what we would do is we go up 12. Our shear diagram is going to look something like that. So that value right there is 12 kips, and that value right there is minus 12 kips. So my maximum shear would be one of these two values. Take the absolute value. Well, absolute value of 12 is 12. Absolute value of minus 12 is 12. So it doesn't really matter which value we use. So if I gave you a beam, a piece of wood, and it was Douglas fir, we would go in the appendix, and we would see that the shear stress that it can resist is 180 psi. But then we would also need to look at what shear is actually being applied to the beam. And that's where it comes from, that V value right there. So we would have, to design what size beam we would need, we would take 180, and we'd set it equal to the maximum shear. The maximum shear is 12 kips. I would divide that by an area, and I multiply this by 1.5. Now 1.5 is just the multiplier that we get. So then, remember, this was in PSI. This is in kips. So I need to multiply this by 1,000, so we're in pounds and not in kips anymore. So I back calculate out for A, and A needs to be greater than or equal to 100 square inches. So if we go through our tables, we can see any beam that has an area greater than 100 square inches would work. Well, we flip through. A 6 by 20 would actually work for this beam here. But if you remember from the previous class when we solved this same problem for bending, we actually needed to use a 10 by 18. So the 10 by 18 would still govern from the bending, but we needed to just double check what value we needed to use for shear.